Hello students, in this video we are going to learn assembly line balancing. The term assembly line refers to the progressive assembly linked by some material handling device. The most commonly used material handling device is the moving conveyor, and on this moving conveyor you must have seen in some automobile manufacturing videos. The job will continuously pass on this moving conveyor, and every workstation will perform the jobs assigned, the tasks assigned to it. So basically the most common assembly line is a moving conveyor that passes a series of workstation in a uniform time interval called the workstation cycle time. Workstation cycle time is also the time between successive units coming off the end of the line. So if you are standing at the end of this conveyor, moving conveyor, and you are monitoring the time between successive finished products coming out of this moving conveyor, the difference between the two successive units on an average will be the workstation cycle time. The precedence relationship is the required order in which the task must be performed in an assembly process, because there is a particular sequence in which the assembly should take place. So that is given by the precedence relationship. Assembly line balancing involves assigning tasks to a series of workstations so that the required cycle time is met and the idle time is minimized. So which station will do which job, and in one particular workstations how many different jobs will be done. The whole decision making is called as the assembly line balancing. The required cycle time C is actually the arrived at production time per day divided by the required output per day in units. So it will be minutes per unit or seconds per unit. The theoretical minimum number of stations NT which are required is given by the sum of task times divided by the cycle time. Rules for task assignment to workstations. There are various different rules which can be used. For example, giving preference to the task with the longest task time, giving preference to the task with maximum following tasks or maximum followers, etc. Efficiency is equal to the sum of the task times T divided by the actual number of workstations into the workstation cycle time. Now let us understand these calculations involved in assembly line balancing through an example from Jacobs, page number 176. The example goes like this. The model J wagon is to be assembled on a conveyor belt. 500 wagons are required per day. So this is our production target. 500 wagons in a day. Production time per day is 420 minutes. The assembly steps and the times for wagon are given in a exhibit 8.9a which we'll see. So we need to balance the line so that it minimizes the number of workstations as well as minimizes the idle time, right? But we have to make sure that the cycle time and the precedence constraints are adhered to. Okay, so these are the details of each and every step. For example, task A is positioning rear axle support and hand fasten 4 screws to the nuts, etc., which takes 45 seconds, and it can be the starting task. Similarly, task D can be also the starting task as no precedence is mentioned, and it takes 50 seconds, and this is the task: position front axle assembly and hand fasten the 4 screws and nuts. So like this, description of each task is given. Task B requires 11 seconds and it can be done only after task A is done. Task C takes 9 seconds and it can be done only after task B is done. Likewise, other tasks are mentioned and their precedence requirement is also mentioned. Task J is the task which takes 8 seconds and it is done only after F, G, H and I are completed. And the final task is K, which is taking 9 seconds, which is tightening of bolts and nuts, and it can be done only after the J is completed. So this is the details of the time, task times and the precedence requirements of all the tasks. The total task time for one wagon, completing one wagon, is 195 seconds when you add all the task times, right? So based on this precedence relationships and these task times, a precedence graph or precedence diagram is developed here. So it clearly shows A and D can be started without without any requirement. We can start immediately, and P can be done only after A, C can be done after B and all that, and J will be done only when F, G, H, I is finished. It takes 8 seconds, and then last activity K, which takes 9 seconds, right? So this is a precedence diagram. Please do not confuse this with the critical path method and all that. There is no relationship between the two methods. Now we move on to calculate a cycle time which every workstation must adhere to. Every workstation can run either the same time or less than this time. How to arrive at that? Total production time available is 420 minutes into 60 seconds, and the output per day is 500 wagon, which is the output target. So when we do this, we get 50.4 seconds per cycle or per wagon. This is what is the required cycle time. Unless we do our every station works at less than or equal to 50.4 seconds, we will not be able to meet this target. So based on this, the theoretical number of workstations, because we have 195 seconds as the total task time and cycle time is 50.4, when we divide it by that, you get 3.87, which is approximately 4. So minimum 4 workstations are required to finish the assembly and meet the cycle time. Now, deciding on the task assignment rules, the author has given us the primary rule as give preference to the task with maximum followers, and in case there is a tie in the primary rules between the two tasks, then secondary rule is available, which is give preference to the task with longest task time, right? So based on this primary rule, if you look at this precedence diagram, say for example A has followers 1, 2, 3, 4, 5 and 6. So A has 6 followers, B has 5 followers, C has 4 followers, D has 1, 2, 3, 4, 5 followers. So like this, for every task the number of followers are first captured so that it helps us in our primary rule allocation. So this is the table. The secondary rule for which is based on the task times is already available in this diagram. The task times are available in case there is a tie in the primary rule, right? So now we are set to start allocating the various tasks, keeping in mind 50.4 is the cycle time and the precedence relationship which is clearly mentioned here. So with that, in our first workstation we can have which activity. So for that we need to first look at our primary rule. So give preference to the task with maximum followers. So obviously A will be the first task to be allocated to first workstation because it has the maximum followers, right? So in our table, station 1 will be having first task as A. Task time is 45 seconds, right? So the idle remaining time or idle time, no, remaining time is 5.4, which is 50.4 cycle time minus 45. Now in 5.4 we can we put B, activity B? No, because it requires 11 seconds. We cannot also put D. So hence this 5.4 seconds will go as idle. So first station will have 5.4 idle time and no feasible remaining tasks can be put in station 1. Station 2, obviously we can put either D or B, right? We can put D or B, but when there is a tie we have to look at the cycle time. The cycle time maximum is of D, hence we put D in our second workstation, right? So it will require 50 seconds and then the remaining time will be zero point 0.4 and nothing can be done in 0.4 and has no feasible remaining task, and this will also go as idle time. Now when we come to the station 3, obviously the B is the first task because it has maximum followers of 5, right? So it will take 11 seconds. After that 50.4 minus 11, 39.4 seconds will be remaining. Now what are the feasible tasks after B? If you look at this diagram, after B you can do C, or we have finished D, so we can do E. So C and E. So C and E both have same number of followers, 1 2 3 4, 1 2 3 4. But because E has maximum cycle time or maximum task time 15 seconds, obviously E will be our choice as the second task in station 3. So E, it takes 15 seconds, 39.4 minus 15, 24.4 remaining. Now C, H and I are the feasible remaining tasks. Task with most follower is C, and hence the next task which will be put in station 3 will be C. So 9 seconds it will take, 15.4 seconds is remaining. Now F, G, H, I are the feasible remaining tasks. All are having the same followers, number of followers, that is 3, and all are also having the same task time. If you see, right, F, G, H, I both are having 2 followers each, and all are of 12 seconds. So anyone randomly we can choose and put. So they have put F, right, which is 12 seconds, and 3.4 seconds remaining, which is cannot be further utilized, and it will go as idle time. Likewise in station 4 we can put any of the G, H, I. So we'll put G, and then we'll put H, and then we'll put I, because H, I and I will be the feasible task, and accordingly 12 12 12 14.4, then J will be put 8 seconds, so 6.4 will remain as idle time, and station 5, then we have to uh, go for station 5. So station 4 are 4 number of stations are not sufficient. Last activity will be done in station 5, which will take 9 seconds, and unfortunately in station 5 41.4 idle seconds will be there. So this is how we will be balancing the line. We following the rules. If the rules change, there may be a different combination available here, but right now our required rules, as per the following the required rules, we get this as the line balancing. Now once we do this, actually if you put it as the workstations here, first workstation A, second workstation D, third workstation B, E, C, F, that is the third workstation, fourth workstation H, I, J, G and J, and the fifth workstation is 5. Workstation 5 is K, 9 seconds. So with this, now we come to the final calculations, that is the efficiency of this balanced line. It is given by T divided by actual workstation into cycle time. So 195 is the time divided by 5 into 50.4, and this efficiency is coming to around 77%. So this is how we do the line balancing as per the given precedence diagram or precedence requirement, as well as the primary and secondary rules of the task selection. Thank you.